Wishing you all a very warm welcome to all the dignitaries viewing this video today. Firstly, we would like to introduce ourselves. We are Team 444-271.
My name is Bhai Roshan from Techno India, third year, EC department, third year.
I am Zoe Bakhtar, currently studying Techno India Salt Lake, ECE, third year.
I am Wahid Hussain. Currently, I am studying in Techno India Salt Lake, ECE department, third year.
My name is Tariq Anwar. I am studying in Techno India Salt Lake, EC, third year.
So, the presentation for today is on the 6th edition of Nginx, which is based on the Digital Twin Challenge, and the vertical under which we are working is Smart Healthcare, and the solution is myocardial ages. The first question that comes in anyone's mind is, what is myocardial ages? So, talking about the terminology, myocardial ages, it is of two words, myocardial and ages. What myocardial means or refers is basically heart or heart tissues and muscles, whereas ages means packing, protection or shielding. So, altogether, myocardial ages means protective cushion or shielding to our heart. Then, if we talk about the idea of myocardial ages, then I would say that myocardial ages is a variable that could be worn by individuals. And the notion which we bring up is that there are sensors embedded on this myocardial ages, which would sense the data that gives emphasis to the foremost signs of heart diseases. Let me tell you, these sensors will not only sense, but they gather and record the data and continuously send them to cloud and also to the twin. Whereas the twin will monitor and it will statistically simulate it so as to predict the heart disease beforehand, where in the real life the physical entity is going on with its work. So up next, we're having our objectives. And in the objectives, we have smart monitoring done by our myocardial ages or the digital twin. Then we have the statistical scrutiny and simulation of the data done by our solution. Then with which it will predict diseases, heart diseases such as myocardial infarction. Then with the help of machine learning, it will predict some other diseases related to heart such as syncope and heart stroke. Then up next, why would one go with our solution, myocardial ages? Why would one switch to this rather than the traditional ways? So we have the answer. So the answer is quite simple if you go with the answers. I am reminded of a proverb which goes as, prevention is better than cure. Yes, it is. Prevention is always better than cure, because preventing a disease before happening is far better than curing it. As next we have, there are very less chances that to find necessary remedy for the cure. Then we can have that the prediction or the detection of the disease happen at a very late stage, with which the likelihood of curing it is way much more less. Then if we do a statistical analysis, not only in India but all over the world, every year about 30 to 35% people only die due to various heart diseases. With heart disease so impactful, all the tests, treatments, medications, diagnosis and every other thing related to such diseases are way much costlier. Such as the poor people die, not only them, but people in the mediocre level, the middle level people also die with these diseases. So we bring up our solution of digital twin myocardial ages, which parallelly runs with mathematical modeling and machine learning. So it is the better or the best possibility to tackle such diseases.
Now I'll be explaining the architecture of our solution. You can see the figure is demonstrated above. I'll be beginning with the physical system we are working on, that is the heart. The sensors will take the values from the heart, and the values would be of multi-lead ECG, systolic and diastolic blood pressure, and accelerometer and gyroscope values will be sent to the cloud using Raspberry Pi 3 model. The digital twin would get these values from the cloud and would simulate the data and will produce a response which will be sent back to the cloud and also to the user. The user will then act accordingly according to the output of the digital twin. The doctor here will have complete access to the cloud as well as the digital twin. It can provide custom values and also simulate it to check if the patient or the user can handle extreme conditions. The family members will always get the real-time values of the patient. The insurance company will only have access to the historical data and trends so that it can dynamically set its insurance premium. And in case of emergency, or we can say that if any abnormal cases arises and the digital twin senses any abnormal cases, then it directly contacts the nearby hospital and it checks for any available beds, and it also contacts the ambulance in case of emergency. Now next we are coming into the flowchart of our solution. The flowchart is quite similar to the architecture I have explained just now. You can see that the vest is implemented on the patient, and then the sensor values will be uploaded to the cloud. The digital twin will be updated and it will get the values from the cloud, and it will test the model with the trained ML model already on it. The response will be either if the abnormal condition arises or not. If the abnormal condition arises, then the patient will be informed and its family member will also be informed, and it will check if the solution is controllable or not. If the solution isn't controllable, then it will check the nearby hospital for available beds and also call for ambulance. But if the solution is controllable, then it will contact the reference doctor and ask for any activity or command if it sends. It will complete the command and it will go back to the loop where the sensor values will again be uploaded to the cloud. This infinity loop demonstrates our solution. The next we are having the tools we are using in our machine learning model. The first one being the MATLAB. MATLAB is a very powerful platform. It provides digital filtering and digital signal processing, and also various mathematical functions which we can use from it. The second is the statistics and machine learning toolbox, which is implemented in MATLAB. It will help us to produce models based on machine learning. And the third, we are having Arduino. We are using Arduino basically to get the values from the sensors and provide it to MATLAB. The next, we are coming in machine learning. So before saying what is machine learning, I would like to say that why we are using machine learning in this example. Machine learning is used in cases where human coding of a function or a mathematical function cannot be demonstrated of a complex object. Like in case of a heart cannot be functionally modeled. It can only be modeled through machine learning, and the only limitation of a machine learning is we require a large set of data. Now we can see the machine learning is classified into two categories. The first one is the supervised learning and the second one is the unsupervised learning. The supervised learning is a model in which we expect an output from the model, and the unsupervised learning is the one in which we don't expect an output. The supervised learning has two algorithms, the first one being the classification and the second one being the regression. In the classification there are only finite number of unique classes in which a data is to be classified, but the regression is the output is a real number, like it predicts the output according to the past data. The unsupervised learning is the only algorithm is there is clustering, in which a large data set is clustered into small data sets, and it can be used for data analytics and also for search engines. The next, we have the steps required for machine learning modeling. The first one being the access and explore data. Now we can access and explore data from various ways. The first one is being through the files, through the database, and also through sensors. Now this data has to be pre-processed so that to remove the noise and also the high frequency component, and now this pre-processed data can be used as data to develop predictive models. The predictive models which will have to be fitting well to the data, and we have to avoid overfitting also. And at the last, we have to integrate analytics and system so that we can export a working model of our system for normal people to use it and predict heart diseases.
Now, we will be training the machine learning model for the prediction of different type of heart diseases. The dataset which we have used is stored in the data folder and is taken from the PhysioNet database. The PhysioNet database has a record of all type of ECG data and health data and other data we can find. We have used a toolbox named WFDB toolbox from MATLAB and Octave. This WFDB to mat function helps us to convert a .data record file located on the PhysioNet server and loads it into a MATLAB file. I have already loaded this data of each record into its corresponding MATLAB file and stored in the data folder. The main program we find here is the final script, which will be loading on the MATLAB. We will be adding the paths to the helper functions and the data, and we are going to visualize a signal to see what it looks like. So this is the signal from the database 01911M, and we are plotting only a part of the sample data. You can see that the three ECGs are plotted together. If we zoom in, these three are very clear. The signal contains of a row vectors of different data and the 3 column vectors for 3 ECG signals. Next, we're going to extract the features from these signals. The feature extraction process is a very long and it takes time. So I've already prepared a feature table which requires only the reference table as an input. You see that the reference table is just the input. The other inputs are the window length. I'm giving 10 seconds for one window length and with no overlap. So let me show you the reference table first. The reference table here contains the first column as the record names of the database and the second column as the response. The response 0 corresponds to the normal behavior, 1 corresponds to myocardial infarction, the second corresponds to syncope, and the third to stroke. So if we run this section, we get a feature table consisting of 49,207 datas and 40 columns. Out of these 40 columns, the 39 are different features of the signal, and the 40th column is the class which determines the normal or different type of heart disease. The next step, after the feature table is ready, we are going to train a classifier. Since we have already coded a line which would train a classifier automatically, but I will train it manually here. The classification learner apps opens and we could import a new session here. You can see that it automatically selects the feature table and sets all the 39 features as predictors and the last one as response. We're going to select a holdout validation and scale it up to 50%. Since we have a lot of data, we can use 50% of the data for training and the other 50% as testing. We're going to start the session. Now we see here different algorithms by which we can train a machine learning model. So I'm going to train some models first. Find KNN first. So we can see this k nearest neighbor algorithm produces an accuracy of 98%. And if we look at the confusion matrix, we can see that the diagonal is pretty good, but the misclassification costs are more, especially in this case where the stroke is predicted as normal, which shouldn't happen. So we're going to train some more models and see what we get. We can see that the accuracy here is 99.1% and the confusion matrix is pretty good. Let's train one more model and then we'll compare the results. See that 3 models are trained of different algorithms: k, nearest neighbor, an ensemble, and a support vector machine. The accuracies are demonstrated here. And the confusion matrix, you can see that there is quite a high misclassification costs. But if we look at this model ensemble and we look at the true positive rates, we see that most of the data is classified right with accuracy up to 99%, and the misclassification accuracy is less than 1%. So we're going to export this model to the workspace with name train classifier. Now we can see this model has come into a workspace. Now we're going to prepare the test data by which we're going to test this model. We can see that the reference table test was already there, and using that reference table test we have created a feature table test consisting of the same 40 columns but only 4,000 data. We're gonna predict this feature table tests using the train classifier and store it in a output yfit. The yfit here we can see contains of all the output responses of the data we have given. And finally we are going to visualize each ECG signal with actual values and predicted values. So we can see here that the three ECG signals are plotted with the actual heart disease or output and the prediction of our model. Now we see that in most of the cases it correctly predicts what is happening. So we can say that this model is useful. So we can see that in the most of the cases the model is correctly predicting the output, and hence we have trained a model such that it predicts the heart disease of a human from the ECG signals.
So here we have designed a human activity tracker which will tell us if the patient is running or standing or just lying over there. So it will help us in different situations, like it will enable us to map the physical activity of the system to its digital twin, which will enrich the digital twin experience. It will enable us to predict the critical situation more accurately, because the ECG signals alone are not sufficient. Here we have an example. If we assume that the heartbeat and respiration rate of the patient is increasing gradually, then we cannot say that it's an abnormal situation. If we see the activity from the activity tracker that he is lying or in a stationary, then we can say that it's abnormal. But if we see that he is running, then we can say it's normal, because running itself increases the heartbeat and respiration rate. Next. Also, from the motion sensor values, we can see that if the person fell down from somewhere, so in that situation, we can alarm its family members.
So for the human activity tracker, we have used the dataset from UCI machine learning repository. Here, along with the raw data, we have also got the process data with 561 features. Here in this part, we just loaded the datasets into our workspace, but here it shows only 27 columns, that is 27 features. This is because when we loaded the dataset of 561 features and trained our model, the model's accuracy was very high, but it performed poorly on the test dataset. That is the dataset. The model was very good on the training dataset only. It was not flexible for the outside data, so we had to do something else. We use the feature effectiveness, this function. This function, what it does is it performs feature selection with neighborhood component analysis, and it gave us this plot. Here the main features which were the effective ones are being denoted by this plotting, and we just took those features only. So here is 27 features only. Next we made our final training dataset after doing the selection, and then we trained the model. This is our model after training. Actually, I have used all the algorithms, but here this one is the most accurate. Its confusion matrix is here. So we can see that the diagonal is pretty good, and there was very few misclassification. So this is a good model. Next, all you have to do is the prediction. Next, we just have to plot the data. So actually in load data, I saved all the workspace variables into test set var, and I loaded them in here. Next, here I made a GUI. Here there was 3 subplots, 2 for accelerometer and gyroscope, and then 1 for the digital twin. I used here a geometric twin model, but we are trying to make a 3D model instead.
So, effectiveness. As we mentioned in our use case proposal, according to World Health Organization, worldwide around 32.26% of total deaths are occurred due to cardiovascular disease, or in a simple word I can say that due to heart disease. So, uses of myocardial edges is considerably cost proficient. Consistent reading of everyday work, that is body postures, movement, etc. And the regular monitoring help us to check whether the body is prone to any disturbing or not. The detection of the malady is done beforehand with the help of digital twin and the mathematical modeling. And it is not easier to change our daily habits once the disease is detected. So with this, it continuously monitors and gives us the feedback of everyday activity. So now the cost proficient. The traditional way of heart disease detection is very much costlier. The tests to diagnose heart disease are following, like there are ECG test, stress test, Holter monitoring test, blood test, CT scan, MRI scan. So the next is the range of this test. The estimated range are, like for ECG, the cost is 100 to 500. For stress test, the cost is 800 to 3000 rupees. The Holter monitoring test is 1000 to 4000 rupees. The echo test is 800 to 1500 rupees, and the CT scan is cost around 1000 to 12,000 rupees, and the MRI scan is the cost around 7,000 to 11,000 rupees, and the bypass surgery is very expensive, which costs around 1.75 lakhs to 6 lakhs rupees, and there are also continuous intakes of expensive medicines. So then we are going to use the hardware for the myocardial edges, which are following. Like for the Raspberry Pi 3 model B plus, we the cost is cost of Raspberry Pi 3 model B is 2800. For the body temperature sensor, the cost is 110 rupees. Heartbeat sensors cost 550 rupees. ECG sensor cost 1400 rupees. Pulse sensor is cost 300 rupees. MPU 6050 cost 306 rupees. Blood pressure cost 800 rupees. SpO2 cost 1000 rupees, and we are considering some miscellaneous amount which is 500 rupees. So total cost for our myocardial edges is 7,766 rupees, which we can say that is a negligible as compared to the traditional way of cost of heart disease detection. So the analogy, the statistical analysis between the traditional way of heart disease treatment and the predictable method by our solution, which is myocardial edges. There is a drastic variation between the cost of both the methods. Like as we can see that the myocardial edges cost up to like 8,000 rupees, and whereas the traditional way cost is around 6.5 lakhs rupees. So we all are well matured enough to understand the difference between some thousand and some lakhs. So as already stated that our model is way more economical than the traditional way of heart disease treatment, and things which are prescribed by the doctors to the patient when the heart disease is detected are following. So these are the following in the prescription doctor said to the patient when the disease is detected. And there are a number of daily life tasks, as discussed previously, have to change. It takes an ample amount of time to change or adapt such type of changes in anyone's life. It is very difficult for the patient to quit smoking, alcohol, and bring such type of changes in his or her life. So all these situations can be managed with the help of our digital twin model. As the twin, what does the twin does is it gathers and records the everyday movement and the habits of the patient, and it which would be a daily feedback to the doctor or the person who is really concerned about the health of patient.
So, up next in the next slide, we have the project plans. So, the project plan for the myocardial edges is like that. Myocardial edges has two parts. One is the software part and another one is the hardware part. The software part consists of two parts. There are two twins designed. One is for the heart disease predicting model and the other one is the human activity predicting model. Whereas in the hardware section, there are sensors, various sensors. There are accelerometer, gyroscope, ECG electrodes, GPS sensor, temperature sensor, SpO2, and all these are connected with Raspberry Pi. Whereas in the digital twins, there are two parts. One is data sets, the external data sets, and another one is input. From the Raspberry Pi, all the sensor values are taken and sent to the cloud. Whereas from the cloud, the values are sent as test inputs to the twins. And from there, the two values from the data sets and the inputs are compared. And after the comparison between both the twins, the main value has been predicted and is again sent to the cloud and to the host and the other person. Up next for the project plan, we have, as far as we have seen, there's a quotation from George E.P. Box, as it says that all models are wrong, but some are useful, and what the useful plans are just in slide. As in the diagram we have seen, or the working of the model, the software or the code part is explained of the myocardial ages. What we have seen is the training of the two twins are being done using the external data sets. Then some test data is being provided manually, but in the coming near future, these values will be provided by the sensor data from the hardware. These values are being fetched via cloud, and then the prediction is made, and the final outcome is being sent to the host. These outcomes is being sent to the host, and there are cases such as generalization, overfitting, or underfitting. Up next, we have the optimization of the available funds. The other half, other than the software part, is the hardware section, which is nothing less than the external skeleton of the myocardial ages. And we promise that if funding is allowable funding is given to us, then the external part will be designed easily with certain sensors. And then we have already provided you the optimum quotation earlier.